Okay, welcome to the second lecture in this specialization course. So glad that you found the room. It's not so easy in this maze. We have the lectures here today. We have lectures in K5 tomorrow, 15 to 17. K5, it is just across the road from here into the chemistry building. And B1 you know already. Last time we looked a little bit behind the theory of the Sola algorithm, the projection method, split step method. Quickly repeat it today. And we will continue a little bit with the theory then behind the Sola algorithm and what you need to solve the exercise number 1, which is out. Yeah, we can have a look at it. So, first exercise, you reprogram the MATLAB scripts you have been given to different geometries, different problems, 3 different tasks, and at the end you make one single zip files, everything into one single file and upload it on its learning. So that's it. And you have been given to the 16th of September to finish that one. We will take some time, I think, to do, maybe already tomorrow if you need some guidance, if you have some questions. So you should start peeking into it. So today we start with let's see if we can do this. No, I can't. Well, we'll do it anyway and see what happens. I will start with a little bit numerical theory in general of partial differential equations, how we classify them, then how we can make a discrete version of them to make numerical schemes. So this will now be sort of the quick and dirty, straightforward way to do things with finite differences, just as we have done it, as you have an example with the Sola algorithm. Choice of the different grid systems, what is the location of our unknown, the velocities and pressure, things like that. Also, a heart of the projection method was solving a Poisson equation for the pressure. We saw that last time. I will show it again today. So we start with the classifications. Second order partial differential equations. We classify them. And to find out which class your PDE belongs, you start by comparing a general form. General form, we will have it like this, A, and then double derivative. And as your unknown here, I use a phi, Greek letter phi. It can be anything, velocity, temperature, pressure, and whatever. And then this is B, double derivative, and now with respect to both x and y, and finally double derivative with respect to y. Something like this. And we can have other terms as well, equal to 0. This function f should not contain second order derivatives or higher order, of course not. Second order, these are the possibilities. So here, okay, I'll limit myself here to 2 dimensions, but remember now, x and y doesn't necessarily have to be space. One of them could be time, for instance. So it's a very generic form, so don't limit yourself here to anything. So if a, b and c here are constants, it's a pure linear equation. If they are a, b and c function of x and y, of the dependent variables, sorry, the independent variables, we call it semi-linear. If a, b and c are function of x, y, and the unknown function phi as well, or maybe even first order derivatives of phi, then we call it quasi-linear. And the quasi-linear, that's where we find Navier-Stokes. You have terms looking like this. U, du, dx. You have terms looking like x derivative of rho times u. These types of terms will show up in the Navier-Stokes. Function multiplied with a derivative of function. Derivative of 2 functions multiplied if the density is not a constant. Non-linear terms. So the Navier-Stokes will be quasi-linear. The double derivative in Navier-Stokes, there typically we will have a constant in front of it. Maybe a constant that may change with temperature. Remember the viscosity there, it doesn't have to be constant. In general it will be. So now we seek what we call a characteristic equation. It's a little bit mathematics. It's a probability equation, also called. So we sort of introduce a lambda, which now reads something like this: du dx. Then we can rewrite this equation on the form as an algebraic equation. Lambda square minus b lambda plus c equal to 0. And this has, of course, solutions. Lambda 1, lambda 2 equals b plus minus and so on. You know the recipe from high school. And this now will represent an equation for what we call the characteristic lines, characteristic curves. And here we'll now have 3 possibilities. Equation for characteristic curves. Three possibilities. First one, b minus 4ac is positive. Then you will have 2 real roots, lambda 1 and lambda 2. They are both real. This is what we call a hyperbolic equation. If it's negative, second, So b squared minus 4ac is negative. Okay, then you have the square root of something negative. You will only have imaginary solutions or imaginary roots. Imag roots. This is what we call an elliptic equation. And finally, they're equal to 0. Then you have lambda 1 equals lambda 2 is one single real root. Then parabolic. So this is how we classify our PDEs. So we check the coefficients and see to which family does it belong. Now this is not in the entire truth. We will have equations that are not second order, they are first order only. Still they will belong to one of these. So it's not absolute, but should cover most of them at least. What's interesting for us now is the nature of these equations. What will this imply, especially for the boundary conditions? So we will go through it one by one. Let's see how to do this. We can start with a hyperbolic. Hyperbolic equation. You will then have two real roots. So a classic equation there. Is the one-dimensional wave equation. There, the constant A would be the wave speed and the speed of sound, and U here being the signal, whatever that might be. So this is 1D wave equation. Wave equation. Another one, which also is hyperbolic, du dt plus a du dx equals to 0. That's actually also a hyperbolic equation, although it's only first order. And there you should recognize sort of the first terms in the Navier-Stokes, although here I have a constant a, not a velocity u. So it's a linear advection equation, you might say. Linear advection equation. Just as a couple of examples. Now, for the boundary conditions. Start out with a region in space, time, and x. And say at time equals 0, we know something in a region in space. So that's my initial values. I know what the signal is at these locations at time 0. Now find a solution as time goes. Find how this u changes in space and time. How can we do that? Well, a hyperbolic system, you have two real characteristic curves. So if you look, say, at the boundary here, this information you have here will now travel. It will move with the constant velocity a to the left or to the right. So here you have these characteristic curves. Characteristics. where you will have sort of the angle there given by dx dt, or as we said in general, this lambda dy dx. So here it will be you have the t there and the x, which then represents, the slope will now represent the signal velocity a. You will have the same effect with the linear advection equation. Although there you would then have to say this a can be positive or negative if you want to have it to have the information travel in both directions at the same time. The same goes for all pieces of information here. He will travel to the left and to the right. Also, the first one will travel something like this. So now you can see, where can you find a solution? Well, based on the initial data that we had originally, this entire sector will be influenced. So that's an influence area. If you change any data here, then you will change the solution in this sector, the entire area. But you can't find a solution everywhere here. Say you want to find a solution at this point in space and time. Well, you have some information traveling from here, that's okay, but you are missing something here to the right. So you can't find a solution at that point. We don't have enough initial information. We don't have enough initial boundary values. So the only area where you actually can find a solution will be in this triangle. So that's the solution area. Okay? Of course, if it's a one-dimensional problem, you might have some solid wall somewhere. Say we had a solid wall here, for instance. And then, of course, it's a question, when the signal hits the wall, you will typically get a reflection, and then he will bounce back. Then, of course, the solution area and influence area will now be limited by this boundary, the physical boundary, of course. So, for hyperbolic problems, you can say the information is traveling along these characteristic lines. So typically what you do if you want to find a solution for hyperbolic problems, you rewrite your partial differential equation and look at it in the direction of these characteristic curves. Then a partial differential equation will switch to an ordinary differential equation. So that's how you should solve hyperbolic equations, if they are linear. Non-linear, oh, that's something else. Then you're talking shock waves, stuff like that, not so easy. Then you have to think in terms of these characteristics. Yeah, we will leave it for now. I'll come back to this later when we are talking about the advection equation. Any questions so far? Okay. These names, I should have said earlier, hyperbolic, elliptic, parabolic, is taken from cross-sections from a cone. So it's just a mathematical names. They don't really mean anything with respect to the physics. So they are just names. Okay, let's take the next one, elliptic. And typical elliptic equation, you can have double derivative in both directions equal to 0. Then you have Laplace equation. Or the Poisson equation if you like, not equal to 0, but equal to something else. Here you don't have any real roots, so the information is not traveling along any curves at all. So how do we find a solution? Well, if you have a region in space, then you are going to need boundary conditions all around your domain. So here you have your boundary conditions. Boundary conditions. And the influence area and the solution area is inside. So if you are focusing on one single point inside that area, looking at the solution at one single point, if you change any data on the boundary, just a little bit, this point feel it instantly and will change accordingly. So everything here will be dependent on the entire boundary, you might say. And you can't skip a part here. You can't say this is an opening. I don't know what the value are in this region. Okay, then you can't get a solution. You must have information, boundary conditions all around, or else forget it. Here, we only needed a region in space. And then the solution may be sort of found. You can march it forward in time, at least to some region. Here we don't have time in our equation. It's pure space. So no development, you say, no marching direction for a solution. Any questions to that one? Elliptic? That's okay. And the final one, parabolic. Example equation. We can take one-dimensional diffusion equation. 1D diffusion equation. From the Navier-Stokes, we have time derivative of the velocity equals the viscosity multiplied with the double derivative. Here only one dimension. So that's a parabolic equation. What boundary conditions do we need here? X and t. Well, we need initial conditions. So at time equals 0, we have to know the solution in space. Please. So we sort of differ between what we call boundary conditions and initial conditions. Initial conditions here with respect to time. Initial conditions there. And we are going to need boundary conditions also. Here we are left with some boundaries. With hyperbolic we didn't have to, but with parabolic, yes, we must. We only have one single real root here, so we are going to need information at this location and this location for all times as well. We need the boundary conditions. So here, boundary conditions. And as with the hyperbolic equation system, you can now march your solution forward in time. So if you know the solution at time equals 0, then you can take the next time step. Say I want to have a solution here. What about my one real characteristic curve? How does he look? Well, he's actually a straight line going like this. So you might say the information goes instantly to the entire domain, but with time, now you can march your solution forward. If you know the solution at one time, you can calculate the next one, and then you can calculate the next one, and so on. So you march the solution forward in time, as you also can do with hyperbolic systems. So also here, the solution area and influence area is the same down here. Solution and influence. So that was the parabolic equation system theory. And the equations we are going to fight will typically have the nature of all three at the same time. Thank you very much. So this is going to be messy. So the Navier-Stokes in general have all three natures. The hyperbolic nature, that one we can avoid if we say the density is constant, it's incompressible flow. Then the speed of sound is infinite, so you can't have any shock or anything like that then. So then we are left with parabolic in time, but it still is elliptic in space. Okay. One thing left to say here. When we talk about initial or boundary conditions, how do they look? How can they look? So we say we have to specify a value for the unknown on the boundary. But that's not the entire truth. Boundary conditions. Say we have our unknown function u. We want to find him. And on the boundary, take the simplest one first. U is given. We know the number. It's either a 0 or a constant or some numbers. At least we know them. We know the value on the boundary. Then we call it a Dirichlet condition. That's a Dirichlet boundary condition. Think of it as given the numbers directly, Dirichlet directly. Another type could be a value for, say, the derivative perpendicular to the boundary is given. This is typically something we do if you have an outlet, and then you actually have no idea what the velocity is going to be in the outlet. Then we say something like this. The derivative is going to be 0 at the outlet, meaning the streamlines will sort of be hitting the outlet perpendicular. The flow just goes out. So that's a neat trick if we want something. We have to say something, but we don't really know what. Derivative equal to 0. This is what we call a Neumann condition. And then even also you can have higher order as well. Still Neumann condition. And finally, if you have a mix on a boundary, you have given u and the derivative as well. It's quite rare, but sometimes it happens. It's called a Robin condition. So you should know about it at least. Then you have a combination of constant values plus a derivative of some order. So this is what we mean with the boundary condition. We need to know something. Okay, that was the classification. So let us now just take a quick repetition from last time. That was called the projection method. Or split step, fractional step, and many more names as well. Very, very popular method, very easy to use. And we have narrowed it down to the following 3 points. First point, calculate what we call the U star. That was a tentative velocity field. It's tentative, meaning it's wrong in general, because it's based on the old pressure, meaning the pressure from the previous time step, not the pressure from the new time step as it should have been, but that's one equation with 2 unknowns, so we can't do it. Second step, that was a Poisson equation for the new pressure. Actually, the pressure difference between the new and the old pressure, and this one now should be equal to do we recall here, what was it, rho over delta t, divergence of this tentative velocity field. So we found this equation by some algebraic trick, and also we took the divergence of the entire Navier-Stokes. So that's how this one appeared. And last step, update the new velocity based on U star, and now the new pressure as well. Then you have the correct new velocity. So that was roughly the recipe from last time, from projection method. This equation here, updating this tentative velocity field, that is a parabolic equation. It looks something like this: du dt equals, and then actually just known thing on the other side. So we just update it directly. We need the boundary conditions, of course, and for the first step you need also the initial conditions. But that was not a problem at all. The second equation, this one, this is the Poisson equation for the pressure. That one is elliptic. And that's the problem. Elliptic equations are expensive to solve. They are tricky. So here we are going to blow our CPU. Here we need to crunch some numbers. Finally, the last equation, that was also some variant of the Navier-Stokes. So also just one sweep for updating the unknown. So no problem there. Okay, first step and third step, not a problem. Second step, big problem. So Now we are going to solve an elliptic equation numerically. So we have a test case. Let's see if we can find it. How to solve an elliptic equation numerically. So then I am going to teach you about Newton-Raphson. So Newton-Raphson, it's very old, 1600s numerics. How to find a function of how to find where f of say x equals 0 for x equals what? How to find a 0 point in a function. And here we have f, and here then we have x, and our function may go something like this. We don't know. Of course, if you plot it, it's very easy to find the 0. So this is, of course, the solution that we are seeking. But how to do this numerically? You start by guessing a solution. Here, x number 1. And then you go up here, and then you read something that is not 0. Okay, we haven't found the solution yet. How to find a better x? Well, you also there find the derivative of the function with respect to x, and then you choose this one as number 2. This is x number 2. And so you continue all the way down until you have a function value as close to 0 as you would like. So the recipe, x number n plus 1, so n here meaning the iteration number, is based on the previous iteration, and then minus the value, last function value, and then divided by the derivative with respect to x at that location. So this is the classic Newton-Raphson. When you have a function changing with only one variable. Well, when we have an equation such as this one, we are going to make a discrete version out of it. I'll look at that later on. Finite differences. So we will have a function. My f here is going to be a function of a whole bunch of unknowns, not just one x. So we have to modify this Newton-Raphson a little bit. Modified Newton-Raphson. So we have an f, which is now a function of many unknowns. Say, whatever should we call them? U. It can be u1, u2 and un, I don't know how many you want, equal to 0. You write it on the form equal to 0. And here it can be many. Not thousands, but it could be 5 or 4 or 10, depending on how you create your discrete equations, your algebraic equations. You will see an example later on. So, how will the recipe now look? Well, you have to pick one of these u's as sort of your focus point, the center point. So here I just call him number I. And I want a better guess than the previous one. A better guess so that my function f is closer to 0 than it was before. So how should he look now? It will still be negative. And then you have your entire f of all these u's, and here you now create a gradient, the derivative of f with respect to the one you have picked out, and here I have picked out number I, u I. So this will be the recipe. And of course here you have to do this many times, and you have to do it for all the different unknowns u. If you have 1000 of them, you have to do this 1000 times for iteration number n, and then 1000 times more for next iteration, and so on and so forth. So it's a very simple recipe, but it works. We also have some dirty trick. We can make this algorithm faster. Faster convergence with a relaxation factor. Relaxation factor. Omega. So the recipe then will be exactly the same. And then we say omega, and just multiply the last term with this omega. dy. Omega should be between 1 and 2 in general. This is actually the recipe for a whole family of iterative techniques. So it's quite famous. You have something called Jacobi and something called Gauss-Seidel. You better write it down. Jacobi iterations. Jacobi, there you only use old values. Only old values to the left, sorry, to the right. I mean, to the right of the equation sign, everything inside here, this f function, the derivative, everything should be based on old values only. That is Jacobi. Then you will have Gauss-Seidel. There you don't use just old values, because when you do this for all i's, meaning for all your unknowns throughout your domain, then inside this recipe here, you will then have u1, 2, 3, 4. Some of them will have been just have been updated. So you will have a possibility here of a mix, some old values and some with just been updated, since you have to go through the entire domain. So what should we say? Use updated values. Updated values directly. We will see an example how this is done in the next lecture. When you want to play around with this omega factor and it's bigger than 1, you will have a surprise if you have programmed it with Jacobi. It will blow up in your face immediately. So then it has to be Gauss-Seidel if you want an omega bigger than 1. You'll see later. With omega bigger than 1, we call this one an SOR, successive over-relaxation. It's a very easy method to program, quite popular since it's so easy. It's not the most efficient method, but normally it works quite fine. So you'll see an example in the next lecture. Any questions? Then we take a break.